These are the instructor's notes for ISBT211 Instrumentation and Measurement Fall 2019, Module 3, Stochastic Modeling and Chromatography. As it says here in the laboratory handout, we are going to be modeling the process of either high-performance liquid chromatography, HPLC, or gas chromatography, GC, using LabVIEW as our modeling system. We're going to model this process using a stochastic model, which is how chromatography is properly modeled, as opposed to a stochastic, strike that, as a deterministic model, which is when we actually calculate the exact answer. So we're going to be using and incorporating a bit of chance, random numbers. We're actually going to have the computer roll some dice inside the program to show that how random chance and probabilities can be used to model things. The background for the lab, of course, is here in the chromatography handout, but this actually refers back to what we've been talking about inside class. If I jump over here to the Prezi that we used for Module 3 in chromatography, what we're really going to be doing is we're going to be modeling this process inside LabVIEW. The thought is that we have a stationary phase. In this case, it is polar water, or normal phase. And then we're going to have a sample that's at the front of the column. And then we're going to place onto it a mobile phase. In this case, it's going to be a nonpolar oil phase, if you will. And at every position along this stationary phase, as the mobile phase flows over it or flows by it in this cartoon, the sample components will have an opportunity to either leave the stationary phase and get on board the mobile phase and move, or they can prefer to stay in the stationary phase and not move, hence the term stationary phase. It completely depends on the probability of how much time they spend by chance moving versus how much time by chance they spend stationary, and that's what actually causes the separation between multiple components. The way this works is that different components have different probabilities to be or find themselves in the mobile phase versus the stationary phase. Depending on the actual characteristics, these probabilities are pretty steadfast. They're usually based on a few things. It could include temperature. It most often involves polarity. In this case, we're just going to be using simple components like A, B, and C. We're not going to name them as chemicals, so we don't need to know their exact polarity or their exact boiling point or the exact temperature of the column. What we're going to do is we're going to generically use a term that is used in chromatography, and that is the affinity or the friendliness or the likelihood that an individual component will leave the stationary phase, dissolve into the mobile phase, and then the mobile phase is moving and move it down the column. So as our cartoon was presented inside class, the way this works is eventually the samples find themselves riding the bus, if you will, or riding this mobile phase. They eventually get to the end of the column, and then what we do instrumentation-wise is we place a detector at the end of the column so that it can see the components. And then when the components, quote-unquote, win the race or finish the race, the detector lets us know that they're there. And depending on how fast they win the race or run the race, different components will make it to the end of the race distance at different times. And of course, that's how this entire thing is going to work. So that's pretty much it for the end of our introduction. So following along in the laboratory handout, we're literally going to go into phase 1 here. We're going to create a LabVIEW VI that simulates the movement of this chromatographic sample component along the column based on random roll of simulated dice and a value of affinity for the mobile phase. So in this first part, we're going to create a sub-VI that's going to be used by our larger VI, and it is simply going to be called move component. What we're going to do is we're going to simulate the possibility or the probability or the likelihood that a component will stay in the stationary phase and not move for this turn or this round of the simulation, or if it will go into the mobile phase and move for this turn or this round of the simulation. Everything in this handout is specifically laid out step by step by step, including where to wire things and where to find the individual values. So it should be straightforward. If you happen to get lost, please refer back to the last step that you finished. It sort of helps to work this with a partner. The way we normally do this is one partner is reading these steps out loud one by one. Perhaps he has some sort of pen or pencil and marks off the steps as they are completed. And then another person is driving, actually moving the mouse and making the LabVIEW code. This takes a little bit, so sometimes partners find it useful to switch out. One person reads, one person does LabVIEW, and then switching out and trading places depending on who gets tired first, reading instructions or clicking on LabVIEW. So let's see if we can get this to work. I need to get rid of this handout, so I'm going to refer to the handout that I'm holding physically in my hand, but I'm just going to read exactly what is in there. So for now, I plan to open LabVIEW and create a new LabVIEW VI, and then I'm going to go ahead and save it because we are working on Windows, and unfortunately Windows has a horrible propensity to just crash for no reason at all. So I am going to save it as movecomponent.vi in the 2019 ISBT211 folder on the C drive of the Windows machine. So I'm going to go ahead and do that. So let me minimize that. We're done with that. I'll go over here to my Windows machine, and I'm going to find LabVIEW under N for National Instruments LabVIEW. I have a couple versions installed. I'm going to install LabVIEW 2019. I'm going to push the button, wait for this guy to come up. There she is, LabVIEW 2019. And again, I'm just going to follow the exact instructions as they appear inside the handout. Wait for my machine to get its stuff together and bring up. Well, we are going to create a new VI. So File, New VI. I'm going to save it right away. I'm going to File, save this VI. And I want to go to this PC, and I want to go to the Windows drive. And I want to go to 2019-11. Here's the previous VIs that we used in last week's lab, and I'd like to call this movecomponent.vi. I need to use two hands here. Move component, if I can spell it right, component.vi. The .vi is already there. I'm going to go ahead and capitalize my M to make it look awesome. And we're good. Okay, so we're in. We have our front panel, as we do with all VIs. I'm going to scooch this over. We have our block diagram, as we do with all VIs. Scooch this over. And see if I can get this guy to move over a little bit. I'm just trying to make them about the same size. There we go. Come on, you. You can do it. Fabulous. Here we go. So I'm just going to go ahead and read exactly the steps out of the thing. Step 2, on the front panel of the new VI, add these three things: a numeric control named Affinity, A-F-F-I-N-I-T-Y, Affinity. Numeric control labeled current position. Numeric control current position. Fantastic. And a numeric indicator labeled new position. Numeric indicator labeled new position. This little sub VI is going to take the current position as if we were playing a game. New position. It's going to roll the dice, and depending on the affinity, the likelihood that it moves or not, it's going to find out if it has win, or if it's a win, or if it's a lose. If it's a win, I guess it moves, and if it's a loss, it stays put. And that's all depend on what number it needs to get from the dice. Okay, our VI should now look similar to the front panel picture below. It sure does. That's exactly what it is. Switch to the block diagram. It's over here. And we need to add the following components. So I'm going to right mouse click and add under the numeric palette, as it says here, random number 0 to 1. So it literally looks like a pair of dice as I find it down here. Random number 0 to 1. Put that somewhere. Go to the comparison palette and get less or equal. Go to the comparison palette, which is there, and go to less or equal. Less or equal is here. Less or equal to, and then go to a structure and get a case structure. Go to structures, get a case structure. There's a for loop, there's a while loop, there's a case structure. Structures are special because you have to draw them. You don't just plop them down. So click a case structure and draw it. Fantastic. As a case structure, it has two, or it can have several, but by default it has two possible cases, either true or false. I'm looking at the false, and now I'm looking at the true. You can't really tell that it has changed. They're both default white right now. And then I also need numeric increment number. So I'm going to right mouse click, go to numeric, and get an increment, which looks like a +1. Here it is, +1. There's our guy. So now we have everything. Let's just go ahead and follow the wiring up. Wire the random number function to the top terminal of the less or equal. So I'm going to go ahead and move these guys out of the way for now. Yeah, I didn't mean to wire that. I wanted to grab it. Okay, so here's my dice. I'm going to roll the dice. I'm going to go ahead and grab the less than or equal to, that guy, and I want to wire my dice to the top of that. I then wish to wire the affinity value to the bottom of that, so go back and grab that affinity again. This is what we're comparing it to. We're going to see, if, based on the affinity, if we roll a dice which is less than or equal to that value. We're going to wire the output of the less or equal function to the input select terminal, this guy here. It's going to find whether we should move or not. If it's true and we've won the dice toss, we're going, or the roll of the dice, we're going to move. And if it's false, if we've lost the dice toss, then we're not going to move. We're going to stay put. Let's see here. Wire the current position value to an input terminal. So here's the current position. We're just going to go ahead and put a tunnel or an input terminal into this box right here. Just drop it right there. That's a little tunnel. And let's see here. Again, I'm just following exactly what it says. Wire the current position value to an input terminal on the left edge of the case structure. We created it by just wiring it to the left edge. Place the increment function into the true case. So there's the true case. I can pull this down and show the false case, or I can just use this arrow. True, false, true, false, true, false. There's true. Put the +1 inside the true case, and I'm now going to turn the page. Wire the output of the increment function to an output terminal on the right edge. So I just go ahead and drop it. I'm going to wire the output over to this guy. Wire the output of the case structure to the new position indicator, which is here. Fabulous. Just following the directions as it says. And then switch to the false case of the case structure and connect the input terminal to the output terminal. So what's going to happen is I need to wire this up here. I need to wire this into the increment. On the false case, it's completely empty because, again, this is true, this is false, this is true, this is false. If it's false, I should not move it. It didn't win the toss. It didn't win the dice roll, so it should not move. So it should stay put. So I'm going to go ahead and wire this just straight through. There we go. So now if it wins, and then the component is able to move down the column. If it loses, then the component does not move down the column. So it should look like this. As according to our values here, it should look like this for true. There we go. That's what it looks like. And it should look like this for false, and it does. There's two different versions of this. There's two different pictures of this in the handout. One is just picturing what it should look like true, and one is just picturing what it should look like false. They're copies of each other. Other than that, I'm going to turn the page, finishing this up. Use test values for the affinity and current position controls to verify that your move component changes the current value by 1 when the dice roll is less than or equal to the affinity value. So let's go ahead and do that. Let's make the affinity 1. So that means that the current position is 0. If I go ahead and run this, the new position is 1. If I make the position 12, say it's on block 12 of the column, and I roll 1, it goes to 13. If I make the affinity 0, it has 0 chance of moving, then it stays at 12. Yep, seems to be working just fine. What we're going to be doing is we're going to be putting in affinities that are probably not 1 and not 0. So this has a 50-50 chance of moving, and you can see that sometimes it moves to 13 and sometimes it moves to 12. It's been sitting at 12 for a while. It moved back. Wonderful. We want to turn this into a sub VI, so we need to go ahead and change its icon, and we want to go ahead and change the connector. So I'm going to change the icon. I'm going to go to edit icon. We did this last week, so this is a repeat of that. The way I suggest doing it is grab the lasso, select all the guts of the existing, leaving the border, and then hit delete. That's deleted now. I probably want to fill this with white paint, so I'm going to click on the foreground color and go to white and grab the paint bucket. Now it's filled with paint. And as I have in here, I'm going to go to my tool. Where am I going to go here? I believe, icon text, that's what I wanted. What I can do is I'm just going to go ahead and line one text. I'm going to put in move, M-O-V-E. There it is. I think I can move that up. Is that true? Use the caret. I can't use this. I'm using the I'm using this way to do it rather than drawing in the middle. So I typed move in the middle, and that's fine. I can move it up if I go ahead and use the select tool and select it and move it up. Nope, that just is this. What if I go ahead? I thought I could cut it. Maybe I can't. Oh, there's the hand. Nope. This is not what I want. I want the move up top. Let's go ahead and figure this out. I'm going to undo the move. So then I'm just going to go to text, perhaps. I'll go back to templates. That's fine. File. I want to see where the text is. Tools, layers, help. If I click on text, do I get a text value here? I'm going to type in move, M-O-V-E. Oh, it's white. I'm writing in white because I'm an idiot. Control Z. I'm going to go here and go back to, say, black again. Try this again. M-O-V-E. There it is. And now I can move it over. That's what I wanted. So here's move. It's towards the top. And then my suggested guy here is really, really impressive. I just take two lines and make it look like a column. There's one line. There's another line. And then I think I made this a different color. I'm going to use the pencil now. I'm just going to have a component look like a drop inside here. I messed that up. If I click this again, I believe I can turn it to, I can't. I need to turn this guy to black, and then I can make that there. And then I had an arrow. This is really impressive, Bill. I'm going to go ahead and do this and make an arrow out of this guy. There we go. 1, 2, 1, 2, and then 1, 2, 3, and then 1, 2, 3. Fantastic. That's awesome. Say okay. It changes this guy to move. And then I happen to have, using the mouse, let's see, right click on step 14, right click the connector of your VI and do the 2 input 1 output. Okay, so up here, right mouse click, go to patterns. I want 2 inputs 1 output, which looks like this guy. I think last week we used 1 input 1 output. 2 inputs 2 output. I want this guy to be the affinity. I want this guy to be the current position, and I want this guy to be the new position. Yep. Connect affinity to the top left, connect current position to the bottom left, and new position, and then save your VI. So file, save, and that is the end of step 1. Fantastic. So welcome to part 2. We need to create a LabVIEW VI that simulates the detection of a sample component as it passes the detector that is located at position 100 on the time axis of our chromatogram simulation. So this is what we'll be doing here. That's what our front panel is going to look like, and then this is what our code will look like. It looks pretty simple. I'm going to make a really, really fancy icon, and we're going to save it again. So it's sort of the same thing, a second sub VI. So this is my old sub VI move component. I don't need this guy anymore. Wait for LabVIEW to come back up. I want a new VI. Going to do this again. Move this one over. Move this one over. Going to resize them. Here we go. And here we we go. Hold on. There we go. Fabulous. You can do it. There we go. Okay. Just following it. Create a new VI, save it. We did that. So file, save. We just made move component VI. I want to call this Chromatography Detector VI. I need to find the keyboard. Chromatography Detector. There we go. .vi. Okay, we're saved. Following the directions, please add an array, matrix, and cluster. Okay, so go to array, matrix, and cluster, which is here. Let's find this. Let's see here. Front panel, array, control enabled. So where are we at? Oh, you know what? They've changed it since 2019. I'm glad I checked this. I will update the the handout. It is no longer called an array, matrix, and cluster menu. It's called the data containers menu. Data containers palette. There we go. Something changed for 2009. I'll change that. We want to get an array. Here's an array. Grab it and pop it down, and we're going to call it components. COMPONENTS. Fabulous. And we need to place a numeric. I think that's still true. Numeric control inside the components array. So numeric control, we're going to click it, and then we're going to place it inside the components. So an array happens to be able to hold, it's a container. That's why they have the new layer called a container. We're not going to put it out here. We're going to put it inside the components. We did that. So that thing resizes because now it contains an array. If I grab this fill handle, there's a whole bunch of them. That's what an array is. An array is a whole collection of identical items. Fantastic. And then I want a numeric indicator as before. Right mouse click, numeric indicator, just like last time. We're going to call that guy detector. D-E-T-E-C-T-O-R. Wonderful. Fantastic. Switch to the block diagram. We're there. Here's the components. Here's the detector. Fabulous. Please grab the following components on the comparison menu. Equal. Okay. Comparison menu equal. There it is, the first one. Fantastic. On the Boolean, grab or array elements. This is and array elements. We want to or array elements. That's this guy. And we need on the numeric, we need numeric constant, and adjust its value to 100. I happen to grab the integer one, the blue one. That's fine. You could put in the purple. You could put in the orange one and make it 100.0, but I'm going to use the blue one. And we need another case structure. Structures, case. Draw the case structure. Again, it will have true and it will have false. Place a numeric constant into the true case of the case structure. Okay. Oh, place another one. Place a numeric constant into the true case, so the true can adjust the value to 1. So we need this guy. Numeric constant again, and adjust its value to 1. Did that. Place a numeric constant into the false case and adjust its value to 0. So go to the false case, grab a numeric constant, and adjust its value to 0. It turns out that 0 is the answer. So what's going to happen is when the detector sees a component, it's going to output a 1, and when it does not see a component, it's going to output a 0. So we're back in the true case here. Let's see here. Wire the components control to the top of the equals function. So here's the components control to the top of the equals function. Did that. Wire the constant 100 value down here to the bottom of the equals function. What we want to do is we want to see if any of these components is sitting at the 100 or the finish line, the 100 step or the 100 square of the chromatographic column. Wire the output of the equal function to the input of the or array elements function. What this guy does is this sees if any one of them is equal. They don't all have to be as in an and. This is an or. And then wire this to the output of the output of this guy to the input of the case statement, which we did there. Wire the constant 1 value in the true case to an output terminal. Will do. There we go. I need to flip the page. Keep on going. Wire the constant 0 to the same tunnel or terminal in the false case. Switch to false. Take 0 and put this guy out, and then wire that to the detector. So the way this works is, and again this is different than what it shows in here, the way this works is if any of our components happen to be at 100, then this detector will say, yep, I see somebody. So let's test this. I'm going to file, save it. I'm going to go ahead and put a component in here at 50 and put another component at 60. And then I'm going to go ahead and press run, and no one's at the detector. I'm going to change this 60 to 100, so that one's at the finish line, and it does see it. Fantastic. If I put 2 of them at 100, I still get a 1. It doesn't say there's 2. It only turns into a 1 if any of them is at 100. If none of them are at 100, there's 0 and there's a 5, then none of them are there. That's cool. It seems to work just fine. Wonderful. Super. Edit the icon of your chromatography detector to show something that represents a component passing the detector. My version is below. Please use your talents. Fantastic. So what I need to do is go over here and edit the icon. And I couldn't fit detector in there. Again, I always like to go ahead and subtract what's already there and hit delete. I like to fill this with white background. Did that. I want to type detector. So go ahead and say D. I'm still white because I'm an idiot. I keep on changing this back. Change it back to black. D-E-T-E-C. Move this over. That's what I did last time. There's detect, and then I couldn't fit Tor. Come down here, T-O-R, and move this over to detector. And then I went ahead and grabbed, if I go here to glyphs, I can look in camera. There it is. Wonderful. That's this guy. I'm going to grab this camera. I'm going to click it and stick it inside here. Oh, I can flip it too. I think I can Control Z. What's going on? Control Z. I think if I push this button, it'll flip it. Is that right? What does it say? What did it say to do? It says rescan glyphs. I think I can flip these things. Anyway, it is what it is. There it is. I don't need to flip it. Oh, I can. I can click it, and it's still selected. I can go ahead and use this command. Oh, it flips the entire thing. That's fine. I don't know why I want the detector facing this way. I'll put it back where it was. Wonderful. That's really awesome. That took way too much time. And then I need to hook this up with one input, one output. So right mouse click, go to patterns, one input, one output. The one input is the components, and the one output is the detector. In file, save. There we go. Save your VI. That is step number 2. Okay, step 3. We're going to create LabVIEW that simulates chromatographic separation of 3 sample components and displays their detection on the chart. So this is our main VI, and we're going to use our previous 2 sub-VIs. So here's the instructions. I'm going to read this along. This is what our VI is going to look like. We'll be able to enter the affinities for 3 separate components and then watch their behavior as the chromatograph detects at what time these individual components meet step 100. This is 100 steps or 100 seconds, not 100 positions. That's our goal. So here's all the instructions. Every instruction is specifically laid out, and here's what it will look like when you're done. So we have this to look at as well. And again, my detector was backwards, but this is how it should work. So what I'm going to do is switch over to LabVIEW and use my my paper copy and see what happens. I'll minimize this guy. I've already opened LabVIEW. I already created a new VI. We know the drill. I do want to save this again, so File, Save, and I want to save it as not Untitled 3, the third one we did. I want to call this Chromatography Sim. So Chromatography Sim.vi. Okay, it is. There we are. Okay, let's see what we can do. On the front panel, a numeric control labeled Comp A Affinity. So here we go. Numeric control comp, as in component, A Affinity. And I should probably make this larger to fit. And I need to add another one next to it called component B Affinity. Fabulous. Make that a little bit bigger. If I can grab it. There we go. And a third one. Numeric control component C. A, B, C. I know how to spell Affinity. Actually, I don't know how to spell. But I very seldomly know how to say the alphabet. Comp 1, 2, and 3. Fantastic. And then a waveform chart. So right mouse click, go to graph, and the first one's waveform chart, and I want to put it right underneath there, and I'm going to make it pretty big. I have a lot of room on this monitor, something like that. And the waveform chart is going to be called chromatogram. Specific enough. Chromatogram. That is what the output of a chromatography machine looks like. I need to adjust a few things. Let's see here. Double click on the y-axis values to change the range to min 0. So double click down here and make that 0. And make the max. Double click, make that 2. Click somewhere else. Right click on the y-axis and make sure the auto scale y is unchecked. I want to lose the auto scale. I want it to stay 0 to 2. Double click on the x-axis and change the range to min 0. Max 200. Right now it's max 100. 200. And again, I also want to turn off the auto scale. So right mouse click and auto scale X is off. That's fine. As far as what I don't think I can change how many of these guys, how many ticks I see here. Let's see what happens. Marker spacing. There we go. Arbitrary. Nah, let's just leave it at uniform. There we go. For some reason, if I made it arbitrary and came back to uniform, it filled things in. That's kind of cool. I'll leave that there. In fact, I just didn't even read my own instructions. Right-click, and then right-click, it says right there, right-click on the y-axis and set the marking spacing to arbitrary. Okay, marker spacing arbitrary. Cool. And then right-click on the x-axis and set the marking spaces to uniform. This will display the scale markings on the bottom of the graph. There you go. Fantastic. That's exactly what I wanted. I should have read my own freaking directions. It should look similar to the picture, and it sure does. That's fantastic. Switch to the block diagram. It's over here. I'm going to move some things out of the way. Move this here and move this here. I didn't mean to wire it. Move that out. Great. Add the following components. A numeric constant. Adjust the value to 200. Okay, right mouse click, numeric, constant, adjust the value to 200. Gotcha. A numeric constant, adjust the value to 100. Okay, numeric, constant, adjust the value to 100. Done. Numeric, constant, adjust the value to 0. Numeric, constant, it already is 0. I'll leave it there. I'm going to grab these guys, just move them out of the way for now. If I remember the picture, I think I remember what it looks like. A for loop. So I'm going to right mouse click, go to structures. I don't want a case structure, I want a for loop. I'm going to draw this big for loop. There we go. Fabulous. Use the select a VI menu item to place 3 copies of your move component VI inside the for loop. Okay, so right mouse click, go down here to select a VI. and grab the move component and say, okay, I'm going to place the first one there. And then do that 2 more times because we're going to move each of our components, component A, component B, and component C. So select a VI, and we can use the exact same code over and over and over again, just like we have multiple constants, and we can use multiple copies of the add function. We're going to use multiple copies of our move component. It doesn't matter. They're all independent of each other, which is fantastic. Right-click on the left edge of the for loop and select Add a Shift Register. Okay, here we go. So right over here, I'm going to right-mouse click and add a shift register. And then repeat the step above, step 5, 2 more times, leave a total. So we're going to make a shift register for component B, and we're going to make a shift register for component C. That's what we're actually doing here. It's going to keep track of where all of our components are. We're going to place an array build function inside the for loop. Okay, so right mouse click. I'm going to go over here to array, and I'm going to grab array build array. There it is. I'm going to put that down there. Let me look at my picture ahead of time so I know where these things are supposed to go. I'm trying to page my page. Yeah, that is down there below there. I was right. There we go. Fantastic. I move this down here. Could put our build array down there. Fantastic. Use the select menu item to grab your chromatography detector. So I'm going to right mouse click, select a VI, go get our detector. Okay, and put it over there. Wonderful. Place a timing wait until next multiple function inside the for loop. So go to the timing, which has a wristwatch. Go to wait until next multiple. Stick it in there. Move the waveform chart indicator into the for loop. So it's here. And there it is. Right click on the chromatograph waveform chart and select create property node history. So right mouse click. See if it gets to work. We're going to create a property node, and what property do we want to actually work with? We want to work with history. As soon as I find this thing, are they alphabetical? A, B, C, D, E, F, G. There's history data. I think I just want history. Let's find it. So property node up here. Bounds position, blinking, control index, disabled. Down here. Legend. Plot. I'm looking for it. Update mode. What's history data? Let's see here. Property node. Oh, I'm sorry. I'm an idiot. It says create property node history data from the menu. That's where history data. There it is. And we're going to put it over here. Wonderful. I got my stuff finally there. Place the property node just created outside. We did that. It's out here. Right click on the word history and use change to right. So right here and call this change to right. There it is. Fantastic. Right click on the input terminal of history and use create constant. So I'm going to right mouse click and create a constant. Create a constant. There it is. Wonderful. Wire the output terminal of the 200 constant to the end. So this 200 that's sort of in the way, I'm going to move it up here and make that the counter of our loop. We're going to run our chromatograph for 200 rolls of the dice, if you will. Wire the output terminal of the 0 constant to the input terminal of each of the shift registers. Okay, I'm going to close that notification on my window. Wire the output terminal to each okay, gotcha. So this 0, what we want to do is we want to set all of these components to the 0 or the starting point. So this guy, and copy this, and this guy, and copy this, and that guy. Fantastic. Wire the output terminal of comp A Affinity, which is there, to an input terminal on the left edge. I can do that. Wonderful. And then flipping the page to step 18. As soon as I flip the page, you can do it, Bill. Wire the output terminal of comp B to the left edge. Okay. And I'm crossing these lines, but that's fine. And then how about comp C? Do the exact same thing. So A, B, and C. Wonderful. Wire the output terminal of the top shift register to the top input terminal of your first mover function. Remember, this guy has two inputs, the affinity and the current position. What it says here, wire the output terminal of the top shift register to the top input terminal of your wire the output of the top input terminal. I think I have these backwards. I have the affinity being the top and the current position being the bottom. Let me go back and check what we were supposed to do. I don't like to read my own instructions. It says here, make affinity the top left input. That's true. So I have this backwards. I will change this. I'm reading bad instructions. What we want to do is we want the affinity to go into the affinity. That makes sense. And we want the affinity to go into the affinity. And we want the affinity to go into the affinity. And we want the position to go in the position. And the position to go in the position. And the position to go in the position. I have this incorrectly labeled on my current copy of the instructions. I will fix that before I hand them out, so they'll be right. We did all of that. There you go. Using the blue handle on the bottom of the build array function, pull it down so you have three inputs. Right now we have one input. I'm going to grab the bottom handle. It really is blue, but it's really small. 1, 2, 3. So that was 47. I want 3. You can see the blue handle now. What I want to do is I want to take these new positions and I want to stack them into the 1, 2, and 3 inputs of this build array. Fabulous. We did that. Wire the output of your build array function to the input of your detector. Remember, our detector is going to look at all of the positions one at a time. And we do this. We give it all the positions at the same time. It will look at them one at a time. And then the output is going to say either I see one or I don't. That's fabulous. And our 100, which we haven't used yet, goes over here to the 100 of our wait for next millisecond multiple to slow down our entire value here. Your VI should look similar to the block diagram below, and it does. In fact, this is exactly how it should look. I just have those words upside down. Affinity really does go to the top, and current position really does go to the bottom. It just happens to be backwards in my version. I will make that better. And gosh, save the VI. Oh, I forgot to do one thing. Do I have... Did I forget to do this? Let me look at this. I believe I forgot to say... We're not done yet because there is a broken arrow up here. We need to take this latest version of our current position and run these through to the shift register on the opposite side. It looks as if I forgot to say that inside the instructions. I will add that as well. Let me go ahead and make a note to myself. Add, update, shift register. Fantastic. I will fix that and we'll be good to go. So yeah, we are set. So yeah, save it up. File, save. And we are finished with step 3. All right, so we're ready for part 4, actually using our simulation to simulate things. I use the phrase experimenting with our chromatographic simulator. It's very, very similar to creating a simulation or a model of a hurricane and then adjusting values to see if you can get better predictions and get better models. In this case, we have built a virtual chromatography machine inside whatever space you want. You can call this some sort of VR machine. You can call it Minecraft. You can call it whatever I don't know, Red versus Blue, Halo Wars or something like that. That's a really old reference. But we're going to go ahead and use our chromatograph to see if we can learn something about what happens when we change the affinity of these individual components. So yeah, let's go ahead and do this. So we're going to follow these steps that I have in my handout, which I have already fixed. And then I go back here to LabVIEW. Let me grab both of these windows. There we are. So step 1, set the value of comp A, comp B, and component C all to 1. So it's going to use the 1 button here. So they all have a component 1. Remember, the affinity is what is the likelihood, or the affinity. Affinity means friendliness. What is the coziness? What is the likelihood that the sample, component A, component B, component C, those components, if given a chance, will jump into the mobile phase? And right now it's 100% or 1. So if we go ahead and press this button, down here you're seeing nothing happening at the detector. We're letting the chromatogram run. This is 100 down here. And then at 100, all of a sudden we see a peak. So this is called a peak. It sort of looks like a little tiny mountain, and nothing happens until 200, and this thing will stop. So it's all finished. It's fantastic. So we only get one peak. So the question here is, how many peaks are visible on the chromatogram? We only get one peak. The simulation contains 3 components, component A, component B, and component C. But we only get one peak, even though there's 3 components that we're seeing. At what time do the peaks appear on the chromatogram? They're all appearing at near 100 or 99. It's not a mystery. What's happening is, remember, our detector is only responding 1 if it sees a component. Even if it sees all 3 components, it only outputs a 1. This is a very rudimentary simulation. We don't have higher peaks because there's more components there. We could go back and we can change that to output a number that adds all of them up. But for now, we're just going to have one value for each of these guys. Let's go back and set the leave A at 1. Let's change component B to 0.9, and let's change component C to 0.8. So now they really do have different affinities. Again, component A always rides with the mobile phase because it's 100% mixed in it. B only rides the mobile phase 90% of the time, and component C only rides the mobile phase 80% of the time. So let's push the button. It blanks it out. That was this guy over here. When we add 0 to the history, it blanks it for us. Let's see what we get. So we're waiting around. There's a component where we had it before, and we get 3 components. The fact that the peaks are wider or not really depends on the roll of the dice. Remember that we're talking about the chances of it actually moving off of the detector as it moves. Because there's only an 80% chance that it will move, sometimes component C will just sit on the detector 20% of the time, so it looks like it's a much wider peak. But now we have 3 peaks. We expected to see 3 peaks because we had 3 components. Because they all have different affinities, since this is the highest affinity, we know this is component A, we know this is component B, and we know this is component C. So that works out pretty well. Question 5, how many peaks? There are 3. At what time do the peaks appear in the result? So again, around 99, around 105, and around 115. Set the values to 1, 0.6, and 0.4. Okay. How about 0.6 and way down here at 0.4. All right. And we run the chromatogram, and we're watching our detector again. Our detector's just sitting there, letting us know when it sees somebody. All right, there's our 1, and we're still waiting for another peak. There's peak 2 at 0.6, and the experiment's over. We only have 2 peaks. How many peaks are visible? We only have 2. Again, the simulation contains 3 components, A, B, and C. At what time do the peaks appear on the chromatogram? This is A, because it's the highest. This is B, way down here at 0.6. This guy, 0.4, it looks as if our simulation finished before point 4 ever got off the column. It was spending so much time, pardon me, so much time in the stationary phase that it didn't have a chance to win the race and get detected. This actually happens for real inside chromatographs. We can adjust how long the chromatogram, quote unquote, should run. It's usually not this fast. Sometimes it's 20 minutes or 30 minutes or maybe even an hour. And if you have very, very slow components that spend most of their time on the stationary phase and very limited amount of time in the mobile phase, they, quote unquote, won't come off the column. The worst thing that can happen, obviously, is that there's a chemical reaction where the component literally glues itself to the column and never comes off. Sometimes in a real situation, after working a column for quite some time, you would go ahead and you would pick a whole series of solvents that are known to flush or known to wipe off or clean off the stationary phase, and you would reconstitute your column. So the last thing here is I'm asking you guys to do. I'm not going to do this, so this is the challenge. Now that you know that the code looks like this, again, this is component A, component B, component C, and we have inputs of each of these affinities. We have zeros attaching to all of their positions. We have 3 copies of the move command. We went ahead and we added all 3 into a build array and sent it to the detector. Question 10, I'm asking you to modify this code to simulate the separation of 4 components. How could you add a D component? So I'm asking you to go over here and add a component D affinity, and then inside the code, over here, Windows block diagram, inside the code, I'd like you to add the appropriate sub-VIs and change the wiring to see if you can go ahead and make a simulation with 4 and then show that to your instructor and save it on the Windows C drive. And I think that will do it for Module 3, Stochastic Modeling and Chromatography. Thanks for playing along.